Okay, and we're back with lesson 2, 8.2, permutations. And we're going to go over a couple definitions. And after this lesson, we'll do combinations, which is a whole different story. So for today, what a permutation actually is basically when you have an arrangement of objects where they're placed in a distinct order. Okay, so this is really important because if you find out that maybe order doesn't matter, then it's not a permutation. So an example might be like if you're arranging letters or digits or people in a row, then every arrangement's different. Right? If you have person A, B, C sitting in a row in that order, that's different than doing it in reverse and having C, B, A. But if you're maybe just interested in drawing colored balls out of a hat, and you get white, red, blue, it doesn't matter the order that you get those balls, you have the same 3 balls at the end. Okay, so one of those situations is a permutation where the order actually matters, and the other one is where the order doesn't matter, because you have the same set of objects. So that's a combination when the order doesn't matter. So my ball example of pulling balls out of a hat, that would be some sort of combination, because if I get a red one, a blue one, and a white one, it doesn't matter what order I get them out of the hat. It just matters that I have that group of colored balls at the end. Or when you have people sitting in a row, that's going to be a permutation, because the order they sit in makes it a different, order, right? Different group of people, so to speak. All right. You also might think of it like a combination lock or something like that. So if the code is 456 and you enter 654, even though you got the right digits, you don't have it in the right order. All right. So basically, one way to remember it is that permutations tell you all the possible ways of doing something. Okay. All right. So a couple examples that we can look at. How many ways can we arrange 5 people in a row? Well, fair enough. So we got 5 people. So for the first person, we got 5 choices. For the next person, we got 4. And it's going to be multiplication happening here. And then for the last option, we have 3 people. This is the fundamental counting principle. I'm going to sneeze. There is a formula that you can use for a permutation. So you can get the same result. The way that it looks, the way it's written is little 5 and then a big P and a 3. And that means, I'm halfway through a sneeze here. So that means that you got 5 objects taken 3 at a time. And this is the result. So you do 5 factorial, which is, of course, 120. And then 5 minus 3 factorial is 2 factorial, or 2. So as you can see, you're going to get the same answer as above, which is 60 ways. Right, and we didn't really quite fill that in, but right above here, if you multiply this out, you will get to 60. So you can use the fundamental counting principle. You've been doing it already, so this is basically a permutation. But if you want a shortcut and you got your calculator, you can actually go 5p3, meaning you have 5 objects and you're taking 3 at a time. Obviously, that'll be handy. You should locate this button on your calculator. It's going to look maybe something like this. So usually it has a small n and an x. Sometimes it's n, p, r, something like that. So look around on your calculator, you can find it. You generally enter this number first, then you hit the button, and then you enter the last number, and then you hit equals. All right. So what is the actual formula for a permutation? Sometimes they get you to simplified, but in general, if you have n objects and you're taking r at a time, then the number of permutations is this. So it's n factorial divided by n minus r factorial, and r is whatever number is here, and n is basically the total number of objects that you have. A couple examples that we can do. So arrangements of the word solid. How many letters are there? Are there any repeating? We got 1, 2, 3, 4, 5. We got 5 letters. Okay, now I'm actually not a huge fan of using permutations. I like doing it this way. So here's my 5-letter word, and I say I got 5 options here, then I got 4, then I got 3, then I got 2, then I got 1. So there's 120 ways. If you do want to use permutations, you should know how. You go 5p5. Now, the reason it's 5p5 is because you have 5 objects, right? These 5 letters, and you're taking 5 at a time. Now, if you type that in on your calculator, you'll get 120. If you use the formula, remember, the formula is n factorial. So that's this 5 over here, divided by n minus r factorial. So n is 5, r is 5. So 5 minus 5 factorial. Now, do not get confused here. because you have 5 factorial divided by 0 factorial. 0 factorial is not 0, it's 1, okay? So you have 120 divided by 1 or 120. So no matter what, you get the right answer. Now for this next one, if you're doing 2-letter arrangements of the word solid, well, you could use a permutation, okay? So maybe take a moment and see if you can get like what permutation would you be using. Maybe pause the video here. So how many objects do you have? You have 5 objects. And you are going to take 2 at a time. So you go 5p2 and get an answer. Or you could do it using the fundamental counting principle and you say, okay, 2-letter words, I have 5 choices here times 4 choices here. So that would be 20. Now, no matter what you do, if you go 5p2, you'll get 20. Or if you do it this way, you'll get 20. Either way works. So that is great news for us. Okay, so do we always need to use the permutation formula? And the answer is, well, no, it's handy, but you don't always need it. And sometimes it's actually really hard to work with it. So if you don't have a calculator, you can think about the restrictions. And we know how to do that using our fundamental counting principle. So in this question here, how many ways can 4 boys and 4 girls sit in a row if the boys and the girls have to alternate? Well, you have to think about it. So there's a couple ways you can do this, right? Like, you got 8 people sitting in a row. So if you go 8 spaces, so there's the 8 spaces. Say you start with a boy. Well, how many boys are there? There's 4. And then you go with a girl because they have to alternate. Well, there's 4 girls. When you get to the second boy, there's only 3 left. And then you get to the second girl, there's only 3 girls left. And so on and so forth. So if you just alternate it like this, it's going to look like this. 2, 2, 1, 1. And just a reminder, I'm not writing it, but it's multiplication all the way through. So basically, you have 4, 3, 2, 1 times 4, 3, 2, 1. So you basically have 4 factorial times 4 factorial. Now, 4 factorial times 4 factorial is 576 ways that you can alternate 4 boys and 4 girls in a row. Now, here's a question. Is there another way you could do this? The answer is yeah. Well, if you take your 8 spaces, what if you started with a girl, right? That would be a completely different way of doing this. So if you go and you do that, just go dot, dot, dot. So if you go and you do it that way, well, the work will be the same, right? There's 4 girls, and then there's 4 boys, and there's 3 girls, and there's 3 boys. So you're still going to get this. So basically, you get 576 again. So now this is the addition principle of the fundamental rule of the fundamental counting principle is you can add up these 2 different cases. So you basically have case number 1 and you have case number 2 over here. So when you add them all up, you get 1,152 ways. Who knew there were so many permutations? There, so there's that many ways of arranging people in a row. Now, what if a boy must sit at each end? Well, this is going to be a little bit trickier. So if a boy sits at each end, remember you got 8 chairs. Okay, so you're going to have a boy here. And then the way I'm going to think of it is here's like the group of 6 chairs. Right, there's going to be 6 chairs, and you don't really care who sits in here. Or maybe we do. Let's reread the question. You got a boy here. Right, so let's see. If a boy's going to sit at each end, when you choose this boy, there's going to be 4 options. And when you choose this boy, there's going to be 3 options. Now, there's 6 more chairs in here, so there's 6 more people. Okay, so basically this is 6 factorial, right? Just imagine. They no longer need to alternate, just the condition is a boy must be at each end, right? You got 8 people, you use 1 here, there's 6 left, so 6 factorial. Okay, so is there any other way to do this? No, because there's a boy at each end. There's no other like case that we can create for this. So it's just 4 times 3 times 6 factorial, which is 720 times 12, because that's what 6 factorial is, and that's what 4 times 3 is. So you get 8,640 ways. Ain't that nice? All right, we're just about done here. What about repetitions? Well, aren't we so happy that we can have repetitions here? Well, we looked at this the other class. How do you deal with repetition? There's a different version of doing this when objects are being grouped together. So let's just start with sort of a basic question, and then we'll just slowly make it harder. How many ways can 5 people be arranged on a bench? Well, again, I like to. That's a really crooked space. I like to write it out. So 1, 2, 3, 4, 5. So here's my first person. There's 5 to pick from. And then 4, and then 3, and then 2, and then 1. So it's basically 5 factorial. So there's 120 ways. Okay. How do you deal with it if 2 of them must sit together? Well, draw your 5 spaces. 1, 2, 3, 4, 5. 2 people must sit together, so draw a box around 2 seats. So for all intents and purposes, if these 2 people must sit together, we sort of consider them as one person. So it's kind of like one unit, and within this unit, there's 2 people. Okay? So, well, how many ways are there? There's 1, 2, 3, 4. There's basically 4 people, so to speak. Okay, so we're going to go 4 factorial. Now, within this group, they can sit together, but they can alternate, right? Like, there's 2 choices here, and then there's 1 choice here. So there's 2 times 1, or 2 ways that can happen. So there you have it. This would be all the ways this can happen. There's 4 factorial times 2 for the 2 different ways you can arrange these people. So there's 48 ways. So that is, if you think of it, sort of like a repetition, right? Where you have these 2 people who have to sit together. What if 2 couples must sit together? Okay, so in part B, we had just basically 1 couple. Now we have 2 couples that want to sit together. Well, again, sketch it out. You got 1, 2, 3, 4, 5. So basically you got these 2 people want to sit together. These 2 people want to sit together. Now remember, each box sort of consider it as one person. So there's 3, 2, 1, or 3 factorial ways that you can choose the different groups. And then within each group, there's 2 times 1 or 2 times 1. So there's 2 factorial ways that we can arrange those people within their own group. Right? Like Jamie could sit here, Jessica could sit here, or Jessica could sit here and Jamie could sit here. So there's 2 factorial ways that can happen, 2 factorial ways that can happen for that couple. So you have 3 factorial times 2 factorial times 2 factorial, which is 24. Now, the last question is one of the trickiest things and you definitely want to remember this. If you have a knot, watch out. Because the easiest way to do a knot is actually going to be the way I'm going to show you. Okay, so if 2 people do not want to sit together, that's actually really hard to think of all the ways that 2 people can't sit together. So what is actually easier is we know that we can take the total ways that everyone can sit together. So total ways everyone can sit together, minus subtract the ways that those 2 people can sit together. And that will give you not together. Now, this is a common trick in probability. It's usually easier to calculate when things are together versus not together. So we did that, right? If 2 people have to sit together, there's 48 ways for that to happen. And we know that in total, for 5 people sitting in a row, there's 120 ways that can happen. So the total ways that everybody can sit together is 120. Right? And then the ways that the 2 people can sit together are 48. So if you go all the ways minus all the ways they can sit together, you will be left with every arrangement where they're not together. And that kind of just makes sense when you think about it. So that's going to be 72 ways. I cannot think of an easier way to calculate that 72. Because you would have to literally think of every way for those 2 people not to sit together. So it's way easier to calculate the ways they can sit together and subtract it from the total number of ways. Okay, so please remember that. Put a star. Maybe pause the video. Try it again on your own. That would be a really good idea. Okay, basically what I have is now a couple more examples that we'll just go through. So take a moment to read through this one. I need to blow my nose. Yeah, I might not edit this out. Man. Because my allergies are out of control today. It's crazy. Okay. So, how many ways can 3 different social studies textbooks, 4 math textbook, 3 science texts, and 2 French texts be arranged on a shelf if the books must stay together by subject? Wow, that is boring. Someone's a nerd. Well, let's see. So what do we got? We got our math books. So math. I'm just going to put math. And then we got our, what's next? I'm just going in order here. We got our science group. Okay. And then we got our French group. And that's, wasn't there another one? Oh, I missed the social studies. 3 different social studies. So we'll just go SS over here, social studies. Okay, so within the group of math textbooks, there's 4 factorial ways you can arrange them, right? So you got your 4 math textbooks. It's like having 4 people sitting in a row. So within that group, I got 4 choices for the first book, 3 choices for the next one, 2, and then 1, okay? Same thing's going to happen with the science textbook. So there's 3 factorial ways within that group that they can sit. For my 2 French texts, there's going to be, guess it, 2 factorial ways. And then for my social studies books, there's 3 of them. So there's 3 factorial ways. Now, this would be one way of arranging on my shelf. So in this arrangement, I got my math books, then my science books, then my French books, and my social studies books. But I can arrange the actual groups, can't I, right? Like I could just take these social study books and put them in front of the math books and have a brand new arrangement, right? So how many different groups are there? There's 1, 2, 3, 4. There's 4 groups. So there's going to be 4 different ways that I can arrange the actual groups. Or actually 4 factorial ways. So I need to multiply by 4 factorial for the actual groups. Just like that. So now when you multiply it all out, you're going to get a ginormous number. It's going to be 41,472. And that's how many different ways you can do that. As far as part B here, if there must be a French text at each end of the shelf, you're going to have to think about it. And your best bet is going to be drawing out a picture. So let's just kind of do, here is our factorial for the groups. And then let's just do our math books. So we know there's 4 factorial ways for the math. And then we had, what did we have? We had science. And there's 3 factorial ways for that. And then we had French. No. French is going to be on either end. So we're going to skip French and we're going to do social studies. Now there's 3 factorial ways for the social studies. And then on each end, you must have your French books. So this is confusing. I'm going to change this to French. I'm going to change this to French. And I'll put some brackets around this. And we'll have to consider how many groups we have in a moment. So how many French books did we have? Well, there's 2 French books. So if there's going to be 1 at each end, when I choose my first French book, I got 2 choices. When I choose my last French book, I got 1. Now, I got to leave the French books at either end, but I can rearrange the math, science, and social study groups. So there's 1, 2, 3 groups I can arrange. So there's going to be 3 factorial ways I can arrange those groups. Now, when you multiply this entire mess together, there's going to be a lot of ways. You're going to get 10,368 ways. So that is a particularly tricky example. And sometimes it shows up on the exam or something similar. So you might want to pause it and try it again. And we are on our last example here, which is, more like our last topic. So if you want to write a title here, you could just write solving my permutation formula. So for solving the permutation formula, sometimes you get questions like this on the exam. So there's an easy version and a hard version. I can't remember which one's which. I believe that this first question is the easier version. So if it says solve NP2 equals 30, you're basically solving for n. So you need to substitute in the definition of this. Now remember, NPR, this is on your formula sheet. It's n factorial divided by n minus r factorial. So I'm going to plug in what I know and set it equal to 30 and try to solve. So I got n factorial in the top. In the bottom, I have n minus 2 factorial, because the 2 right there, and that has to equal 30. Now, we practice getting rid of factorial. So last lesson I said always expand the bigger one first, because we're going to get to n minus 2 eventually. So I'm going to expand the bigger one. I'm going to get n times n minus 1. And now when I get to n minus 2, and then you are going to divide by n minus 2 factorial. So you got n minus 2 factorial on the top and the bottom. So that's going to cancel out to 1. It's also going to get rid of your factorial sign. And now you got n times n minus 1 equal 30. So you can distribute the n into the brackets, and you are going to get n squared minus n equals 30. So I'm going to subtract 30 from both sides, like that, and it's now going to equal 0. So now this is something you can factor. So it's actually quite an involved question. And this is just a regular factoring question. So two numbers that multiply to negative 30 but add up to negative 1. So it's going to be negative 6 and positive 5. And now you can use the zero product property, and you'll get n equals 6, and you'll get n equal negative 5. Now, you do need to check your solutions. The n value has to be at least 1 or bigger, right? Maybe it could be 0. I can't remember. I'll have to look into that. But it definitely can't be negative. So actually, you're going to reject this. And you just have the one answer, n equals 6. Okay. So last but not least, for sure, is the slightly trickier question that they generally don't put on the exam. So is this last one. When you're solving, if you had to solve for the other variable, it would just be harder, as we'll see in a moment. So again, replace the 6pr with the formula. So it's n factorial. So it's 6 factorial divided by n minus r. So 6 minus r factorial. And that equals 30. So now that is the tricky part, is dealing with this, because you'll never get it to cancel with the 6 factorial or anything like that. So what we can do right off the hop is we can cross multiply, and we're going to write 6 factorial. Keep not getting my factorial. So 6 factorial divided by 30 equals 6 minus r factorial. Now, you'll need a calculator, but basically you have 720 divided by 30, which will give you 24. So now the reason this is tricky is because, well, like I said, you can't really solve the factorial. You just have to think. So what factorial is 24? And it turns out that, well, the 6 minus r, that's 4 factorial. So 6 minus r has to equal 4. So if you solve it, you're going to get that r equals 2. And there you have it. So the reason why that one generally doesn't show up on the exam is because of the sort of guess and check nature of the question. So if you do get a question, and it does pop up every now and again, you get one like this first one. This is a question that I've seen on the exam, this first one. All right. So finally, here we are. You can do exercise 8.2. I threw some supplement up on Teams, and also in the description of the video, I will throw those supplemental exercises as well. So thanks for joining me, and we'll see you next time. Bye-bye.